Welcome back, and this is another in our series of videos looking at pH and Ka. So just to remind ourselves, these are the equations that we need to know. Do remember in chemistry you're not given a formula sheet or a formula booklet. You do need to know all of these equations. However, at 298 Kelvin you are given the value for Kw as 1 times 10 to the minus 14. But you do need to know all of these expressions and all of these calculations. So we're going to continue with your notes, and we're looking at the difference in dilution effects of weak and strong acids. So we're looking at page 14 of your notes, and we should in class have done this experiment where we've diluted a strong acid, hydrochloric acid, and we should see that there is a step change in the pH. You might not get these perfect numbers, but you should see there's quite a big increase each time. So when we dilute our acid by a factor of 10, our pH increases by 1. Now, to understand this, we need to remember back to our equation. So hydrochloric acid is a strong acid. The definition of a strong acid is it completely ionizes. So it completely turns into hydrogen ions and chloride ions. To be a little bit more specific, what it will actually do, because remember an acid can't act as an acid without a base present, is the water in the solution will pick up the hydrogen ion and you will have Cl negative. Now this reaction happens to completion. So all of the HCl has dissociated. In other words, there is no HCl left. So when you dilute it by a factor of 10, the pH will go up by 1 because there's no reservoir of hydrogen ions left to dissociate. So that's that one. Now we're going to look at a weak acid. So again, these are my figures. You won't get exactly the same because it depends on the temperature and the absolute concentration of the ethanoic acid. But you can hopefully clearly see there's not the same stepwise reaction here, or there's not the stepwise change here. And again, it comes back to the definition of a weak acid this time. Remember, a weak acid only partially ionizes. So again, if I do the equation, and it's always a good idea to start these expressions with an equation. Remember, it is reversible. So we have CH3COO negative, aqueous, and our hydrogen ions, aqueous. Now notice, this time we have this reversible sign, and also because it's a weak acid, only a little bit of it will ionize. Again, we know that this isn't quite true. So if we put in the full reaction, it's easier to see the role that the water plays in this reaction. And we still get CH3COO negative aqueous, and we get H3O positive aqueous. And obviously water is a liquid. Okay. Now we have a large reservoir of undissociated ethanoic acid. Okay, so remember this equilibrium position lies well over to this side. So we've got a large reservoir of this undissociated acid. Okay, if we add water, this will shift the equilibrium position, remember this is an equilibrium position, forwards, releasing more hydrogen ions. This equilibrium goes forwards, we get more of this. Now that will counteract slightly the dilution effect. Slightly. It doesn't completely counteract it because you'll notice the pH is still increasing. It's just not increasing by as much as the strong acid did. So this counteracts the dilution effect. Okay, so it's very important that you start, personally I would start with this equation because it's better able to explain the role of water. We've got a large reservoir of this undissociated acid because that's what a weak acid does, it only partially ionizes. So if we add extra water, this will drive this reaction forwards. This will release a few more hydrogen ions, enough to counteract that dilution effect. And this is a favourite question in the exam. Another favourite exam question is talking about the enthalpy of neutralization. So to do this, we need to go back to our energetics notes and remember what is the enthalpy of neutralization defined as. So if you remember back to our definition from energetics notes, is the energy release or the enthalpy change when one mole of water is produced by this acid-base reaction, and that's what we're looking for. Now, the question below was an exam question. It was a 6-mark question which came up. First thing to notice is it's not actually the enthalpy of neutralization. This is an enthalpy for reaction for 1 mole of the acid. And then we were given these values. And this question we've broken down into various steps. So the first thing we're going to consider is why HCl and HNO3 have the same enthalpy change of reaction. So the trick to explaining this one is to think what's going on in an ionic equation. So we're going to write out the full equations for these two, then I'm going to turn them into an ionic equation. So I've got HCl, aqueous, and sodium hydroxide, which is also aqueous, reacting together in a 1:1 molar ratio to form H2O, which is liquid, and NaCl, which is aqueous. The other reaction I've got is HNO3 aqueous plus again NaOH aqueous, and this goes again to H2O liquid plus NaNO3 aqueous. Now if I do the ionic equation for this first one, the sodium and the chloride, they are my spectator ions, so I get H positive aqueous plus OH negative aqueous goes to H2O, just about fit that on. And again, if I do that with a second reaction, well, this time the nitrate ions, and again the sodium ions are spectator ions, and you shouldn't be surprised to see that I have the same ionic equation. So actually, in both cases of these two, I'm doing exactly the same reaction. I'm producing 1 mole of water via the same ionic equation. So unsurprisingly, the enthalpy change is the same. So these are both strong monoprotic acids. In other words, they both dissociate 1 hydrogen ion, and they fully dissociate because they're strong acids, and they both react to produce 1 mole of water each via the same equation, hydrogen ions plus OH negative ions going to water. So that explains why they have the same enthalpy change of reaction. So the next question is, why does the ethanoic acid have a lower enthalpy change than all the others? So the first thing you should notice is it's very close to the other two, monoprotic acids, but it's just slightly lower. And again, it's always good to start with a equation for these. So you're still going to get your ethanoic acid, CH3COOH, reacting with your sodium hydroxide to make sodium ethanoate, CH3COO. Negative, Na positive, and H2O. And again, if you were to do the ionic equation for this, I surely should put aqueous under all of these, you would see that it comes out the same as the other two. So it's very close to these ones. However, there is a second, or if you like, first reaction that actually has to go on. So this reaction, this ethanoic acid has to ionize. In other words, you have to get that hydrogen ion away from the salt. And this reaction is very slightly endothermic because you're breaking this bond here. So this reaction to release the hydrogen ions is going to require some energy. So explaining that, It's a weak, again, it's a monoprotic acid, so it has a similar value to the other acids, the other strong monoprotic acids. It's slightly less exothermic as some of that energy is required to break off that hydrogen ion in the first place. And that takes about 2 kilojoules per mole to do that, which is why the difference between those two is 2 kilojoules. So the last question is, why does H2SO4 have such a high enthalpy change of reaction? And it shouldn't surprise you that again we're going to start with an equation, or rather in this case 2 equations. So the H2SO4 dissociates, if you remember, twice. So H2SO4 and sodium hydroxide, NaOH. I need 2 moles of NaOH, and I'm going to make 2 moles of water plus Na2SO4. So because I produce 2 moles of water, I'm going to get nearly double the amount of energy released per mole, because sulfuric acid is a diprotic strong acid. The question then becomes, well, why don't I get exactly double? And the reason for that is something we've talked about before, and that is the fact that the sulfuric acid doesn't dissociate all in one go. It releases its hydrogen ions, if you like, one at a time. So that's the first dissociation. But the second dissociation, you're trying to get a hydrogen ion away from a negatively charged ion, the HSO4 minus. And that should be reversible, and this second reaction is suppressed by the first reaction because you've got a high concentration of hydrogen ions. So there's a couple of things to mention here. One, the fact that this is a diprotic acid, so you're going to make 2 moles of water per mole of acid, but also you don't get exactly double because these 2 ionization has to happen in steps, and the second one is suppressed by this first one. So again, it's this strong diprotic, and sometimes we call dibasic acid, so it produces these 2 moles of water. As we said, it's almost double but not quite, because that second dissociation of sulfuric acid, this reaction here, takes a little bit of energy, because this reaction is a weaker, or HSO4 minus is a weaker acid than H2SO4, so it doesn't ionize as easily. So that finishes this video looking at 2 important exam questions: the effect of dilution on a strong and a weak acid, and the enthalpy of neutralization and reactions between 1 mole of an acid and excess sodium hydroxide. In the last video, we're going to look at how the R group can change the strength of the acid. So until then, take care, stay safe, bye-bye.